We are recording, great. So Monday you have a quiz. Class 32 is your intro to exponential functions, and class 35 was all that compound interest, radioactive decay, growth, all that stuff, all the models we had with that. So and it's just 2 classes, so I don't think it will be a long quiz. I'll probably be making it up at 2:30 today, so I'll try to keep it short for you. Okay, so let's take a look at where we're starting. So can I have someone read this to me? Alexandra, you're used to me, so why don't you start us? Nice big booming voice from the back. Okay? All right. Okay. This is one of my favorite problems because about a year ago I got the New York Times, the magazine, had an article on what's happening to the growth rate in the country of Nigeria, and particularly what's happening in the capital area where most of the population is concentrated in terms of the health conditions, the living conditions, etc. And I gave this article out to my students, and we spent quite a bit of time. I asked them to come in with questions that they'd want to be able to answer, and hopefully we could learn the mathematics before the end of the semester to look at some of those questions. But I don't think a lot of us have a sense of how fast or what it means to be growing at the rate of 2.5%. Just to have some sense of comparison, the US population is growing at less than 1% a year. Okay, so, and I think in my class today I realized I spent about 10 minutes on this and we did a lot, and then we were kind of rushing at the end. So to be faithful to Caitlin, who I know would not be doing this with you, and I can sort of go off and look at these things, but I'd be glad to show you some of the stuff afterwards if you'd like to see it. Let's just try to stick with the question. So right now, we would use our PERT, like the shampoo, the PERT formula here, and we have values for P and we have values for R, and E is a constant, it's a number. Okay, so what can I fill in right now in this formula if I were going to try to solve it? What could I fill in based on the information given? The rate. Okay, so the rate is given as a percentage. So we need to convert the percentage to a decimal, because remember, you can't put in a percent. That's not a number. We have to convert it to a decimal or a fraction. So we have 2.552%. Ooh, I really like writing on the smartboard. It's cool. And that's 0.02552, because you basically divide that number by 100. So it becomes 2 place values smaller when you divide by 100. So right now I know I can point 0.20255 in there. T is what I'm trying to solve for. Okay. Do I know any other pieces to that puzzle there, Alexandra? Okay, and what is that? Okay, right. So P, which is the population, the initial population we're looking at, but it's already grown since the article has been written. Okay, P is 170 million roughly. And then what do I put on this side? That's, am I recording? Yeah, I think I'm recording. Yeah. So T, I'm actually looking for T. I'm looking at how long it's going to take to double, but yeah, so just double it. What does double it mean? What am I doubling? 170. So this is what I'm trying to solve. I'm trying to say, how long is it going to take for the current population, which is expressed here? Well, this is expressing any growth in the population, but particularly how long is it going to take for the value of the population to be 340? We have a problem, Houston. We don't know how to find an answer when your variable is as an exponent. We know how to do lots of things with equations, but how the heck are we going to get it out of there? Okay, so we have to undo this. This is e to a power. We have to undo it because we want the power. Wow, how did that happen? Did I touch it? Whoa, there we go. This is like, I got to watch my body here, huh? Everything. So today we're going to learn, we won't be finishing this problem off today. That will probably be Monday or Wednesday next week. But our goal is how to use algebra to solve this. And I'm still going to show you. Oh, I didn't download GeoGebra, did I? Okay, so what I did for my class is it's so fast to do this in GeoGebra. I put this in, and it's an exponential function like this, and it goes through 0, 170, because 170 is your initial population. So when t is 0, e to the 0 is 1. Any number except for 0 to the 0 power is 1. So that's always where you can tell when you look at your exponential function what the coefficient is right there. Because whatever your y-intercept is, that's the coefficient. And then I said, well, just what would I do if I had a calculator? I'd put this thing into like y1 on my calculator, and I'd put this thing into y2, which is just a horizontal line. But because I didn't have to mess with the window in GeoGebra, and it's really easy to take the axes and expand them, I just decided to throw this in GeoGebra. So then I did a horizontal line across like that. So this was, I just called this like h of x was 340. And this was f of x. And then GeoGebra has a function called intersect. And it found that value right there. And it was roughly 27 years for that to double. Which if you think about cities that are already densely populated, about 24 people live in a room smaller than my office with no running water. Okay? And you think about that population doubling in less than 30 years, which most of you, hopefully, barring any tragedies, will still be alive. It's a serious health problem. It's a serious problem for that country and many countries in sub-Saharan Africa. So we need to do some work as a global community to deal with these situations. But this is the kind of way, this is one of the ways you can use what you're about to learn in the next couple of weeks to answer some of these questions for yourself. Or if you're reading articles, to ask some questions and get the answers. Okay, stop, Linda. Go on with the lesson. I love this stuff, so it's hard for me to stop. So, Jordan, can you read the next one for me, please? Okay, stop. Okay, stop for a minute. Who's the most theatrical in the class? Who do you think? Anybody like into drama and theatrics? And anybody? Okay, then I guess it's you, Jordan. So read this last sentence with like some enthusiasm, like if you were down at Cape Canaveral and you were watching Apollo or something. Yeah, liftoff. So today we're going to do liftoff. We want to lift this off. We want to lift that exponent off and find the value for that exponent. So today we're going to figure out how to do that. Okay? Is this following along with your notes so far? Sometimes Caitlin and I have a little different version. So let me see. I think I stole a packet from my student today so I could have it. Okay. All right, so the next thing we're doing is we're just reviewing what you learned, let's see, or what you were at least exposed to last Wednesday, I believe it was around Wednesday, your basic exponential function. So if we're trying, so let's think of the famous function machine picture. Here's my function f. I put into f some number called x, and out comes 2 to the x. Okay? If I want to find an inverse for this function, and let's see, I scroll over here, I guess, right? If I want to find an inverse for this function, then I have another box called f's inverse. We're going to call that g for today for a reason you'll see later. So what's going to happen if I take the output from my f function? Now remember, this is f inverse. This is really the inverse of f. If I put this in to its inverse function, what's got to come out for my answer? X, right? Because it's the round trip model, right? Round trip. What you started with is what you end up with. That's how all inverses work, okay? So if this thing truly has an inverse, we're going to be able to essentially determine what the exponent is when we put it into our inverse function. That's our goal for today. So how would I know from looking at the graph? Travis, do you know how I would know from looking at the graph whether it has an inverse? Do you remember what helped us with that? You don't. Okay. So to have an inverse, we have to have this property called one-to-oneness. And do you remember what visual thing we can do to see if a graph of a function has the one-to-one quality? Horizontal line test, right? Remember, the vertical line test determines if it's a function, because the vertical line says for every input you have one and only one output. We know we could have oh, I got to be careful here, huh? Oh, okay. I'm so animated, I could really run into trouble here today. Did I just move that whole? I did, didn't I? Woohoo! All right, let's see. I think I can get it back down where it belongs. There we go. Okay. I think I don't know how to make it stay static though. All right. So if we want to know if this has an inverse, we can take any horizontal line, not just one, but any one. And if we draw the horizontal line left to right on our graph, as long as it touches our graph in one spot, then there's one value of x that gives you that output. So this definitely has the one-to-one property. So how do we know? It passes the horizontal line test, which means it's one-to-one. So we know it has an inverse. Okay, so before we can think about what that inverse is going to look like, we know that every function that has an inverse is this really neat thing that happens with the domain and the range, right? The domain of your function becomes the range of your inverse and vice versa. So if we can look at what the domain and range is of this function, we might have a sense of how to graph the inverse function without even knowing what the inverse function is. So Catherine, what would be the domain for the blue function that we've drawn here, 2 to the x? Right, it's all real numbers. So if you want to know a fancy way to say all real numbers, you can do R with like a double stem that says the set of all real numbers. Or because we're all Weber-Sinites, we know we have to use interval notation. So that's the domain. So that domain is going to be the range of F inverse, right? It will be the range. So I know my range can be any number, negative or positive, any number in the world. I'd like to now know what my domain is for my inverse function. So what's the domain going to be for my inverse function? Well, if I can figure out what the range is for my function, I'm okay. So now I can totally ignore anything below the x-axis because this function's never going to be negative. So then I just have to remember, can this function be 0? Can I put some number in for x that makes that 0? No. If you remember, I'm sure Caitlin talked about the x-axis being the horizontal asymptote. Maybe, does that sound familiar? That this gets really, really, really teeny, weeny. And it's like, in theory, if we were drawing it, I mean, our curve would touch the x-axis because we don't have lead in a pencil that's thin enough to show that space. It's never going to get there. It approaches 0, but it never gets there. So how would we represent the range for this function in interval notation? How would I represent the range? That blue line, all the values y could take on f of x. How about in words? What would the range be? Can the range be negative numbers? No. So we can start. Yeah, we can't include 0, but then we can go to, we grow without bound. This thing, the end behavior of this grows without bound as x goes to infinity, and as x goes to negative infinity, this function approaches 0. Okay, so that's the end behavior. So now I know something about the domain of my inverse function. My inverse function will be 0 to infinity. So if, not including 0, so if I were to graph in red, the inverse function. At your seats right now, I'm going to ask you a question, and you can talk it over with your table mates. Catherine can talk to herself or me, or think by on her own and then show me. I want you to tell me what quadrants would contain the graph of my inverse function. What quadrants? If you know this about the domain and this about the range. So which quadrants would my graph pass through? The graph of my inverse. So just jot down whatever you think the answer is. Talk about it real quick with Katrina and Travis. We'll discuss it. James and Alexander, Jordan and Jody, and Catherine will write down her own thoughts, and then I'll check it out. Where's the recorder? Oh. What do you think, Catherine?
I don't know the names, but it's top right.
Top right and bottom left. Yes. Yes. And that's what it looks like. That's called your block. Yes. Mm-hmm. This is, it goes counterclockwise. First, second, third, person. I mean, it's arbitrary, right? Just like north and south. Okay, so do we have any? Okay. So right, 1 and 4. 1 and 4. So your entire function, inverse function, is going to start down here, and it's going to be going up into that quadrant. We don't know the shape yet. You can imagine the shape by maybe some of the stuff that you learned earlier about inverse functions, but at least you know where it's going to appear. Okay, so let's take a look at our liftoff function. So instead of using f inverse, we're going to use the letter g to denote the inverse of 2 to the x. And so again, if we put 3 into our f box, which takes 2 and raises it to the power that we put in, out comes 2 to the third. We now want to take that value. Oh, I love that color. It's not red, it's like a magenta. So we're going to take 2 to the third, and we're going to put it into the G machine, and out comes what? 3. So essentially what we're going to do is we're going to lift off the exponent. So here's our output for our first machine. We put that as input into our second machine called the inverse function, and we're just simply going to lift off the exponent. Da-da-da-da, and we're right back to where we started. We started with 3, we end with 3. Now how simple can that be, right? Hey, we're just lifting off the exponent. So if 5 goes into my F machine, out comes 2 to the 5th. We put 2 to the 5th into the G machine, our inverse machine, and what comes out? 5. Okay, you fill in the next line. Check it, so then I don't have to check. Oh, you can use these things right here. If you have any question, just pop that up and I'll come running to your side. Looks good, Catherine. Okay. Okay, so it looks like we have success as I walked around the room. Does someone want to instruct me? I'll be the writer, what I put into this first blank right here, f of -4. 2 to the -4 says Katrina. Okay, and want to help me finish this, Katrina, so we know that g of 2 to the -4 gives me -4. Right? I just pluck off that exponent. Any questions on that? Okay, let's take a look. So here we have some more, and yep, Jody, yep. Because our f function says to do this. Whatever we put into our f function, how it's defined is the f function is 2 to the power of x. So whatever we put in for x, that's our exponent on 2. Okay, let's just use some language now for a minute, and we call 2 the base, -4 is the exponent. And what would be the result of 2 to the -4? Do you remember? 1 over 2 to the 4th. And how would I simplify that? 1/16. So anytime, well, I won't go there. Right. So let's see if we can go straight across here. I've got 4 of these, and I essentially have 4 tables. Catherine, I'm going to include you with this table right here. So Catherine and Jody and Jordan, what would be my answer for G 5 to the 4? Anyone? G being the inverse of 5 to of. So what would the original function look like? What would f of x look like here? 5 to the x. Right? So if I'm undoing this now, what's my answer? 5. So you're looking at the base, right? And remember, we want to come back. Let's see what this would have looked like. This would have looked like f of 4 is 5 to the 4th, right? So we want to come back to x. So where's x there? Is it the base or the exponent? All right, so I want to try that again. 4, okay. We got that, okay. And Alexandra and James, what about the next one? 2 7s. You agree with that, Alexandra? Okay. And then Travis and Katrina? -2. So I'm just lifting off the exponent. That's all I'm doing. Plucking it right off the base. All right. And then finally, we have 4 to the -1. Linda, would you answer that? Yes, I would. -1. Okay. All right. Okay. So far, so good. No problems. No, you know I'm going to set you up for something, right? I mean, can life be this easy in a math class? Of course it can be. So let's try. All right. Why don't you try that one at your seats? So now she's not done. She said, well, if there's 2 answers, can't be a function. So what's the Math 107 student to do? I'm sure some of you did this and got 1 for an answer. Did anybody write this and get 2 for an answer? I could have also written this. Probably wouldn't think of this, but I'm just showing you. That just says, flip me, take my reciprocal. That's all the power of -1 does. I can make 1,000 of these things, probably an infinite number, just to drive us crazy, but we don't have time. So Catherine's saying, if I have a function and I input 9 into my function, to be a function, I can only go to 1 and only 1 output. Only one output can come out of my function machine. G is a function. And now you're telling me I got 3 different answers. 1, 2, and then the one I dreamed up. I don't know what to do. I know I can't have this situation in a math class if I'm defining a function. So I think I need to add another detail to this function besides just lifting off the exponent. Okay, there's something else that has to happen. Can you figure out what determines what this answer is here? Whether I get 1 for an answer or 2, forget about the one I gave you. The input, yes, the input, specifically what about the input? The input determines it, but if I'm just comparing these two, 3 square and 9 are the same. So what is it about the input that determines that one answer has 1, one of the answers is 1, and one of the answers is 2? Right, so we know that this becomes that, and this one goes there. That's how we get the answer. But what determines whether that's a 2 or a 1? The base. If you knew what the base was, you wouldn't have any decision to make. There wouldn't be duplication or triplicates. It would be very precise. Right now, we're not precise enough because we get more than one answer. So we have to tell the person who's doing this inverse, what base are you looking at? Because if I write 9 with base 3, my answer is 2. If I write 9 as 9 to the first, my answer is 1. If I write 9, not likely, but if I write 9 as 1/9 to the -1, then my answer is -1. I have to have more precision. So we're going to skip the next problem, and we're going to go right in to what we need to do. So Catherine, you want to read that for us?
That last example should convince us that we have a problem. The power that we're going to lift off depends on the base that we use. To denote the base that we're interested in, we'll add a subscript or a liftoff function.
Depends on the base we choose. So we're going to add a subscript to our liftoff function. So if I do something like this, this is called a subscript. That's going to be the base. And I want to replace 16 as something 4 to some power. Now there's no decision to make. It's very precise. There's no ambiguity. So what would I replace 16 with so its base is 4? How could I write 16 so it's 4 to some power? 4 to the second power. Okay. Now I have a power to lift off. It's 2. So that's my answer. Okay. No ambiguity because I'm very clear what my power is. Okay. If I do this, what's my answer? 1. Because the base and the answer are exactly the same. It has to be the power of 1. Can you make up one more for me? Can you make up one more G with a subscript that's different than the one we just did? Any subscript that you can figure out the answer to? 1/2? Ooh, you're getting a little tricky on me there, Alexandra. So what would it be? 1/2 to the what power? -4, right? Because you have to switch your 2 around, your 1/2 around. You have to take the reciprocal. So 1/2 to the -4 power says, find my reciprocal so I can be flip me, and then raise me to the 4th power. So that is the same thing as the number 16. My bases are the same. I lift off my exponent. Okay, we're back to some cool stuff now. We're kind of back to where we were, kind of feeling a little confident that I can just lift off this exponent. Okay? But notice we can only do that because we have this little subscript here. Any questions on that? Okay. So let's see if we can fill the rest of this in. Well, we didn't do G base 2. So this is how I read this now, folks. So my language is G base 2. And when you think of base 2, think of the base of your exponent. G base 2 of 16 equals what? G base 2 of 16 is the same as G base 2 of 2 to the 4th, and that equals 4. G base 4 of 16, I think we just did this one, is 4 squared, which is 2 when I lift off the power. And G, this is the one that Alexandra just did for us. G base 1/2 of 16 is 1/2 to the negative 4 power. I lift off the exponent and get negative 4. Okay? Getting the hang of it? All right. So let's make them a little tougher, but not too bad. Okay. When we had this one, G of 9. Okay, so if we were going to break this out into now that we have this subscript notation, there's a couple of ways we could write this. We could write this as G base 3 of 9, and that would be 2, because I would replace the 9 with a 3 to the 2nd power, okay? If I write it as G base 9 of 9, that's the one you chose, Jody. The base is on both. The base on the inverse function and the answer here are exactly the same, so your answer is 1. Okay? And we could write G of 1/3 as a base if we wanted, and then it would be 1/3 to the negative 2, and then our answer would be 2. So if we went back to 9 as being our input into our inverse function, then we would just get our answer by clearly telling the person doing the inverse what the base is. Right?
But is there a rule about if it doesn't have one listed, then you're supposed to use?
If it doesn't have one listed, we're going to get there because it's a very common base. What's common? Yes, 10. So if you see G, you might as well go there. Since it was asked, why not? Who cares if it's not in order? So if you see G of 100, the base that it's understood to be when you don't see the base is base 10, just like our number system. So you're saying 10 to what power gives me 100? 2. Count your zeros. Hey, can't get much better than that. G of 1,000. Huh? Yep. If you don't see it, it's 10. So what would the answer be? 3. 10 to the 3rd is 1,000. So you can always check yourself by saying take your base, take your answer, go back to your exponent form, and these two things should match. Take your answer, which is just an exponent, your base is 10, there's your 1,000. Okay? So here I'm going to do a little different. What's that going to be? Not -2. How would you read that? How would you write that as a fraction? 0.001. 1/1000th, yes? Which is 10 to what power? What kind of power does it have to be if it's a fraction? Negative. How many zeros on the 1,000? 3. Okay. So we call the inverse function, which we're going to give a name shortly, where the base is not written in. I can't tell you what we call it because then I give away the surprise for today. But I'll come back to this. All right. All right. All right. So this one's a little tougher, but I think we can figure this out because I can already tell from working with you that you're all very bright. So here's a tougher one, but we can figure this out. I could probably have you muck around with it for a few minutes if you wanted. You want to muck around for a few minutes? So we're trying to find the answer here. Let's call the answer y. See if you can figure out what y is, and if you can't, that's okay. We're going to work on it together, but sometimes it's fun to play around with something and see where you might be confused, and you might surprise yourself and not be confused. Want a little help? No? Yeah. So what kind of thing, like, I saw a lot of you really thinking about this, and some people kind of trying to mess around with their calculators, and so I'm just kind of curious what you might have been doing with your calculator. What kind of thing were you doing with your calculator? Catherine, what were you doing? Like that? Okay, because we know, well, it doesn't matter, yeah. We know here 8 is our original exponential function. This is our base. So Catherine said to herself, okay, here's my base. My answer is an exponent. That's all this thing is. It's just a fancy way of writing an exponent. Holy God, why do we have to do all this just to get an exponent? But my answer is an exponent that when I raise 8 to that exponent or that power, this is my result, 16. So, does Caitlin have the graphing calculator on here? She's supposed to. Where is it though? I don't see it. Oh, maybe it's on the desktop. Is it on the desktop? I know she pulls it up, but I don't know where it is. Bummer, maybe. Let's see, calculator here. It's not the TI-83. No, that isn't the TI-80. I have it right on my taskbar all the time. Where does she go in? Do you know? She pokes a few things. Well, let's just use a regular old calculator because it's really, we don't really need a graphing calculator. So if we raise 8, does this even have exponents on it? Where? Oh, thank you. 8 view? Oh, then I can get the scientific one. Okay. So if I say 8, I don't have my glasses on. Where's the little exponent thing? Right there. Raised to the first power, I get 8, right? So I've got to be bigger than 1, right? All right. 8 squared is 64. Oh my God, I'm not even going to be close to being the number 2, right? Because 16's a lot closer to 8 than it is 64, yes? So it's a number between 1 and 2, yeah? So it's got to be a fraction. Okay, so at least we know, darn it, we're not going to get a nice answer here. We're going to get some kind of fraction. Okay, so if and I did this with my class today. This is a little sidebar. You know, when the judge calls the lawyers up and said, let's have a sidebar, we're going to have a little sidebar now. If I said this, 2 to the third equals 2 to the question mark, what would the question mark have to equal? 3. In other words, if your bases are the same and you have an equation to make the left side equal the right side, you just have to set your 2 powers equal. So you would say 3 is equal to the question mark. Guess what? Done. So if I can get an equation where what I have on the left side can be written as an exponential form with the same base as what's on the right side, hey, life gets much simpler. Okay? So you look at the base on the left side and you see the number 8, and you look at the number 16 on the right side and you say, can I rewrite both of those numbers as sum number raised to a power with a common base? 8 and 16. Can you rewrite 8 so it's some number to a power, and then 16 is that same exact number to a different power? 2 to the 4th is 16. And then what about 8? 2 times 2 times 2, 2 to the 3rd. And it has a y beside it. Okay, so there's my 8 and there's my y. Do I have the same bases? Okay, so now all I have to do is solve this equation right here. When does 3 times y equal 4? So I solve this for y. I divide both sides by 3. And there's my fraction, 4/3. So let's check this because I'm still a little weak because it's been since the second class that we've been dealing with rational exponents. So let's take a look at this. 8 to the 4/3. Remember, your roots go in the cellar. If you're from a farming family, you know your roots, potatoes, carrots, beets, they all go in the cellar. So this is your root. And that's what it always is. When the denominator is 1, it's just your power, your exponent. Say our power here. So it's always easier to take the root first. So I take the cubed root of 8, and then I raise it to the 4th power. The cubed root of 8 brings me to 2. 2 to the 4th is 16. I'm a happy camper. Okay? Definitely a happy camper. All right. And to show you that I'm a happy camper, we're going to put a little smiley face right there. All right. So you could start off by estimating like we did with whole numbers. 8 to the 1st is 8. 8 to the 2nd is 64. Oh, crap. I have a fraction. The fraction indicates some root. What root? Well, can't take the square root of 8 and get a rational number. It's got to be the cube root to give you 2. And you can express both 8 and 16 that way. Okay, so this is what you're going to use in filling out the table next. Okay, so let's go through this table. We start off with G. Oh, I forgot to undo my smiley face. Just the regular old pen. Okay. So we're going to start off. This says G base 5 of the number 125. So you rewrite 125 as 5 to some power. You don't have to do much work because you know you can express 125 as 5 to the 3rd. So 5 to the 3rd equals 5 to the y. So we know y is equal to 3. So you're replacing this number with an exponential form that has 5 as the base. It's 5 to the 3rd. Whenever you get your base here and your base here equal, the same, you lift off your exponent. Okay. So let's do the next one. Well, we've done this one. We can kind of, do we know what the answer to the next one is? Yes, no? Without even doing the middle, we can do this. I want to express 9 as 3 to some power. What would that power be? 2. And I lift off my 2 because these two things are now equal. So I'm safe to use my lift off the exponent. As long as my bases are equal, I can lift off the exponent. Okay. The next one, I think, is one of those funny ones Linda was just doing a minute ago. So this is going to take a little more work. So if I follow my middle column, it says 1/16. That's what I have in the parentheses. 1/16 is going to equal, what's my base of my exponent? 8 to some power called y. Now, the minute you see 8 to some power and you get a fraction on the other side, what does it tell you about the value of your exponent? It's negative because you're going to be making a reciprocal here. So the minute you look at this, you say, okay, I'm going to be looking for y as a negative exponent, okay? So before you even start doing any little mathematics, at least you know what your answer is going to be, or part of your answer. So we know that 16 can be written as 2 to a power. So 1 over 16 is 2 to that same power, except for we put a little dash in front of it and make it negative. So this is 2 to the negative 4, and this is 2 cubed times your y. So now you solve for y. You get negative 4, because my bases are the same. Negative 4 equals 3 times y. Y is equal to negative 4/3. So now I go to my last column and I rewrite it. I have g base 8 of 1/16 is written as g base 8, and now I'm obligated in parentheses to put 8, the same exact base, to some power. And over here on my scratch paper, I figured that out to be negative 4/3. And now, because my bases are the same, I lift off my exponent. Okay. And oh, we already did the next one. When we did the base 10, we didn't write it in, right? I didn't mean to do this for you, but I guess I did. So this one says 0.001 equals 1,000th. So 1,000th is equal to 10 to some power. And I think we determined what that power was. What was that power going to be? Negative 3. So g base 10 of 0.001 can be written as g base 10, same base now, 10, but it can't be a positive number because I would get big numbers. It's got to be a fraction. It's got to be negative. And since it's 1,000th, it's 3, negative 3. Okay, so I want you to do the next one at your seats. So far, let's just kind of know what we've done. So far, let's get the highlighter going here. Let's see, the highlighter should be maybe light blue. So when we get over to this right side, as long as this base and this base are identical, we lift off the power. This base and this base is identical, we lift off the power. This base and this base identical, we lift off the power. This base and this base identical, we lift off the power. But notice, these are for specific problems. And this last row here is going to tell you what to do no matter what G is. No matter what B is and no matter what X is. Okay, it's going to tell you how to find the answer. So let's now go to G base 4 of 1. So how can you write 1 as 4 to a power? Because I need to replace 1 here with 4 to a power, because I need to express 1 with that base of 4. So what goes there? 0. Because 4 to the 0 gives you 1. So G base 4 of 1 becomes G base 4, same exact base. The bases are going to be the same. I lift off the exponent. Okay. So now we don't have any specific numbers. We're going to write this using algebra for any possibility. So if this equals y, we know our base is b, we know our exponent is y, and that's going to be equal to whatever x is, b to the y. So now I rewrite what I started off with, g base b of x. I know what x is equal to. It's b to the y. And as long as my bases are equal, I'm right back to where I started with my original exponent on my exponential function. Okay. So in general, this last line, what we did is we said this function base b of x is y when x is equal to b to the y. B to the y gives me x. So, definition, the lift off function can be abbreviated as LOG, base b of x. The lift-off function is what we call the log function. So I had never seen log functions ever presented this way, and I thought it was the coolest thing I've ever seen. I just memorized stuff when I was learning this, and it was like I had one that I always remembered. I always had this one in mind. This is what I always used to put at the top of my paper when I used to take quizzes and tests, because I know 10 squared is 100. So I would say, oh yeah, the answer goes there, and yeah, that thing's the exponent. I would just remember that one thing, never knowing like the relationship between putting it in exponent form and just lifting off the exponent. So in general, we can write a log function as an exponential function once you know the relationship between the two. Notice the base of your log function has to be identical to the base of your exponential function. The answer to your log function, which is the inverse of your exponential function, was the original value you put into your exponential function. And then the result of your log function is the result of your exponential function, or the number you're taking the log of. That's right here. We call this the argument, like later on in trig and stuff, but x there is the answer to your exponential function. So this is your range, it becomes your domain. Okay. So it's a lot of like funky looking letters just to find an exponent. That's all you're doing. Okay. So I think we're almost out of time. We've got 5 minutes. I don't think you'll have any problems with these. These are even easier than the table we just did a minute ago. But I do want to focus on this one right here, F. Focus on what? Yeah, that's where I want to focus. So log function, we said, was the inverse of our exponential function. What two quadrants was our log function located in? First, and the one below it, the fourth. So what has to be true about the domain of our log function? No. The range of e to the x, which is all positive numbers. Here's e to the x or 2 to the x, right? All positive values. If you're in this quadrant, what's true about your x values? All positive, right? Well, they could be 0, but we're not including 0. That's why I have. So the only thing that can go into a log function is a positive number. Just like the only thing that can come out of an exponential function is a positive number. So what the heck are we going to do with this one? What would you do if you put that in your calculator? Try it. You have the log. Oh, you can't do log base 8 yet. Okay. You would get this. It's impossible. I can't take the log of a negative number because I'm only in these two quadrants. All of my input, my domain is positive. Anytime you see a negative number for your log function, you say, okay, Caitlin or Kavanaugh, you're not going to fool me. I know this doesn't have an answer. Okay? So here's where we get to see our graph of our log function. Notice, to do our exponential function 2 to the x, which this is, so let's say f of x is 2 to the x, which is just our doubling function, right? It's going to be there's our doubling function, and notice you have a partner on the opposite side, right? because it's reflects around the line y equals x. So your log function, you can always tell the base of your log function too by looking right here. You go to y equals 1, and it comes back to 2. Because on your exponential function, so this point here is 2, 1. The value on the exponential function, you reverse, and as long as your function goes through 0, 1, that value 2 is your base. So you always go to your 1 on your log function and you can find your base. If you didn't have the picture of your exponential or you didn't draw it yourself, you could always, once you have your log function, you can always just go across that line y equals x and get your exponential to see what your base is. So you'll have lots of practice on drawing those in homework. We don't want to sketch that. Here's what I talked to you a minute ago. Well, we did a little side that if you see log x, it means log base 10 of x. We call this thing the common log. And you have a special button on your calculator. Does anybody have a calculator, graphing calculator with them? Since I can't pull up Caitlin's. So the common log button is LOG. LOG. So if you press LOG, and you put a number in there like 100, which we know the answer is 2 because 10 square, you hit enter, there's your 2. Okay, you put in log of, if you want to find this, log of 0.01, you hit your log button. A little log with a parenthesis comes like that on your calculator screen. You put in 0.01, you don't have to close the parentheses, you hit enter, and what comes out for your answer? -2. So remember, the range of your log can be all real numbers. So you can have negative answers because you can have negative exponents, yes? All right. The other common log, so I think you can go, we can almost do this real quick. Log of 1,000 is log of 1/100th we just did, -2. This one you can only do on your calculator because you're trying to figure out 10 to what power equals 2. So throw that one into your calculator. Log of 2. I don't have a calculator, so what do you get when you get that, Jody? Huh? For this? No, yeah. We're not doing 10 to the second. We're saying log of 2. Okay, so it's approximately 0.301. Do I have a second on that? Anybody? Second. Okay, good. Third. Okay. How about log of -2? Gong. Can't do. Can't take the log of a negative number. Now, how are we going to figure out this next one? Inverse, right. So what's our base? 10. What's our exponent? It's the answer. Every log is an exponent. So now put 10 raised to the 1.8 into your calculator. We're going to get something less than 100 because 10 square is 100. So what's our answer here? $63.096. So I'm going to put little squigglies like that. Okay. And this says go from exponent form to log form. So if I were to write this as a log, I look for my base. It's 10, so I can just write the letters LOG. I don't even have to put the 10, base 10 in. My answer is my input into my log. My exponent is my answer. So these two are equivalent. Okay, and 30 seconds more, please. Please. So the only other log that's really common with a base is if we have log base E. You were introduced to that with the PERT formula that was called the natural exponential function. So you don't write log base E, you just write ln. So lnx means your base is E. So if it helps you to write it in, write it in. If you want to do it, just put your little e there like that. It's redundant, but if it helps you, it's fine. So log base e of 1, you have to write 1 as e to some power, which the only power that gives you 1 is 0, so your answer here is 0. Look, this one's already done for you. You got a base here of e, and you've already got that in exponential form. You just lift off your power 2. You lift off your power 1. This you have to put in your calculator. You have a button called natural log, ln. Notice it's right below your log button. So you hit ln, you throw in the number 15, you hit enter, and out pops 2.70000, right? So approximately 2.7. Voila, answer to this. Error, can't do. And have a wonderful weekend.